In this video, we'll talk about differentiating polynomials and other functions that have variables raised to various kinds of exponents. We've learned about the power rule and how to take the derivative of a constant, and now we're going to use that information and apply it to when we're taking the derivative of something like a polynomial function where you're adding multiple terms. So the sum and difference rule here about differentiating says that the sum of two differentiable functions is differentiable, so you can take the derivative, and it is the sum of the derivatives. So if you have f plus g and you're taking the derivative of that whole thing, it's the same as taking the derivative of each piece. Similarly, if you're taking the derivative of two functions that have been subtracted, it's the equivalent of taking the derivative of each piece. There are product and quotient rules for differentiation, but they work very differently. So this idea only applies to when we're adding or subtracting terms and taking the derivative of that. So let's look at some examples here. Example 4a, we have f of x equals 4x to the third plus 3x squared plus 2. We want to find the derivative, so we're going to take the derivative of each piece. So first take the derivative of 4x to the third. So as a reminder, that coefficient or constant out front we leave as is. We bring down the variable, the exponent, so put a 3 there, times x raised to the 3, there we go, minus 1. So subtract 1 from the exponent. Then for the next term, leave the 3 out front, bring down the exponent, the 2, and then you have x raised to the 2 minus 1 power. And then the final one, the 2, let me choose a different color here to keep these straight. There we go. The 2, the derivative of 2 is 0. So if we want, we could just write 0. Remember, the derivative of any constant is 0. And now we can simplify these. So we've got 4 times 3, that's 12x squared, plus 3 times 2, which is 6, x to the 2 minus 1, that's to the first. You can write to the first power or not, and then plus 0, but we don't really need to write that. So our final answer here is f prime of x equals 12x squared plus 6x. So we found that derivative by taking the derivative of each piece and adding it. So we're going to use the same idea here in B. To find y prime, or dy dx, take the derivative of x to the negative 2, so bring the exponent down, negative 2x raised to the negative 2 minus 1. Then for this next piece, plus 3, so leaving that coefficient or constant out front, bringing down the exponent, and then x to the 5 over 3 minus 1 in the exponent, plus 4, and then bring down the exponent, that's a 1/3, x to the 1/3 minus 1. So simplifying, we get negative 2x to the negative 3, plus this 3 and 3 cancel, giving us 5x, and then 5 over 3 minus 1 gives us 2/3, plus we've got 4 over 3 here, x to the negative 2/3. Okay, so if we're trying to write that nicely, let me see. I'm going to go up above b to write it. So we get dy dx equals negative 2 over x to the third plus 5, and then because we have x to the 2/3, that means we have a cube root of x squared plus 4 over 3, that's this part, and then x to the negative 2/3, that means it's going in the denominator, and it is a cube root of x squared. That's a 2 there. It's a little hard to read. There we go. And that is our derivative for b. Now in C, when we look at this function, it's not set up for us to use the power rule. So we need to rewrite this so we can use the power rule on each piece. Because right now there's division happening between these different variables and terms. So I'm going to take each piece and divide. So this is x cubed divided by x minus 4x divided by x plus 5 divided by x. And that simplifies to x squared minus 4, because our variables here cancel, plus 5x to the negative 1. Okay, so that is f of x. Now we're ready to take the derivative. So f prime of x equals 2x to the 2 minus 1 minus, let's see, we've got negative 4. The derivative of a constant is 0, so I'm just going to put minus 0. And then plus 5 times negative 1, x to the negative 1 minus 1. So altogether, this comes out to be 2x to the 1, but we don't need the 1 power written, minus 5x to the negative 2. Rewriting that one more time, we get 2x minus 5 over x squared. And that is our derivative. Okay, let's take a look at C now. Again, we're going to have to do some simplification before we can start taking the derivative. So as a reminder, the square root of x is the same as x to the 1/2. So when I go to rewrite this, g of x, I've got 2x squared divided by x to the 1/2 minus 3x over x to the 1/2. So now we can simplify. Let me move this so it's a little easier to read. Okay, so we're still doing g of x. We have a 2x squared divided by x to the 1/2. What we're going to do is subtract the exponents. So 2 minus 1/2 leaves you with x to the 3 over 2. And then minus 3, and here we have an x to the 1 divided by x to the 1/2. Subtract those exponents, you get x to the 1/2. So that's just g of x. Now we're ready to take the derivative. So g prime of x, I've got my 2 out front, bring down the exponent, which is 3 over 2, and then x to the 3 over 2 minus 1, minus 3, bring down the 1/2, x to the 1/2 minus 1. A 1/2 minus 1 is a negative 1/2. Okay, so going back to simplify, the 2 and the 2 will cancel, leaving me with 3x to the 1/2 minus 3 over 2 x to the negative 1/2. So let's get rid of that negative exponent and make this x to the 1/2 in the denominator. Okay, so final run through here. We have 3 square root of x minus 3 over 2 square root of x. And that is our derivative. It's our final answer for C. All right, on to E. Taking a look at this, you might think, oh, well, I can take the derivative of x squared, and I know how to take the derivative of 1, etc., but we can't apply the power rule or the constant rule here because we have two sets of parentheses being multiplied. This would need something called the product rule, and we only know about the sum and difference rule. So before we can take the derivative of this, we actually need to multiply all the terms out. And you could do that by FOILing or using a Punnett square. So first, as I'm trying to rewrite g of x, I'm going to multiply x squared times x, which is x cubed. Then I'm going to do x squared times negative 3, so negative 3, negative 3x squared, then 1 times x, so plus 1x, and then 1 times negative 3, negative 3. Okay, we are now ready to take the derivative. So g prime of x is 3x squared minus 3 times 2, because you're bringing down that exponent, x, and that would be 2 minus 1, which is just 1, plus 1, that's this part, it's the slope, plus 0. Oops, right, plus 0, because a constant's derivative is just 0. So simplifying, we get 3x squared minus 6x plus 1, and that is g prime. So the key here was to multiply everything out and then take the derivative. Similarly here, we would have to multiply out x minus 3 times x minus 3 times x minus 3, and once we've done that, then you could take the derivative. That would be a really long process, so we're not going to do that. But the key here is to realize that you can't use the power rule when you have something inside parentheses like this. You can only use the power rule if you have a variable raised to an exponent. Okay, so there are some practice problems here that you could try. The final part we want to wrap up with here is looking at a few key functions that don't fall into the polynomial pattern, or you can't use the power rule for, and that is sine and cosine, and e to the x, and the natural log of x. So this is just something you have to memorize, that the derivative of sine is cosine, and the derivative of cosine is negative sine. So taking a look at 6a here, we're trying to find the derivative y prime or dy dx. That is going to be equal to 2, because just like before, the constant rule has that coefficient out front, and then you just take the derivative of what's left. So the derivative of sine is cosine. Cosine of x. And that is the derivative. That's all there is to it. Okay, in b, we might want to rewrite this before taking the derivative. This is equivalent to 1/2 sine of x. It's like there's an invisible 1 in front of that sign. So now we're ready to take the derivative, y prime or dy dx. Leave that coefficient out front, or that constant out front, and then you're just taking the derivative of sine, which is cosine of x. Okay, now in c, when we do y prime or dy dx, we're going to use the sum and difference rule, take the derivative of each piece. So what's the derivative of x? It's 1, because the slope of x is 1. And then plus cosine. So we want the derivative of cosine. Going back up here, we see it is negative sine of x. And that's the derivative. You took the derivative of both pieces and added or subtracted them together. All right, differentiating e to the x. E to the x is special because the derivative of e to the x is e to the x. It is the only function where the rate of change is identical to the original function. The derivative of the natural log of x, this comes up in calculus a lot. The derivative of the natural log of x is 1 over x. So looking at two examples here in 7a, when we are finding y prime or dy dx, we leave that coefficient out front, that's 5, and then the derivative of e to the x is e to the x. And that's the derivative. In b, when we go to take the derivative, y prime equals 5, and then the derivative of the natural log of x is 1 over x. Multiply that together, and you get 5 over x. And again, we could write it as dy dx or as y prime. And that's it. You are now ready to take derivatives of polynomials, derivatives of terms with other exponents, such as fractional and negative exponents. You can do derivatives with sine and cosine in it, with e to the x and the natural log of x.